Hello everyone, I am Dr. Kairan Mubina, Assistant Professor in Physics, Sadakuzulapa College, Tirunelveli. Have you ever wondered what allows your smartphone and laptop to process information so quickly? Most modern devices rely on millions, even billions of transistors, particularly a MOSFET, a type of FET, or the building block of central processing unit and memory chips. FETs are everywhere. It's a tiny but mighty component. Today explore what a FET is, why it's so important, and how it changed electronics forever. Now we will discuss about the FET, Field Effect Transistor. Before that, we have a short recap of BJT, that is Bipolar Junction Transistor. In our school days, we studied about basics of transistors, right? Transistors have the function of amplifying and switching electrical signals. The BJT, the bipolar junction transistor, it is a three-terminal semiconductor devices. It's called as a bipolar because its operation involves both electrons and holes as charge carriers. It has a three terminals: base, emitter and collector. There are two types of BJT: PNP transistor and NPN transistor. For PNP transistor, the N-type semiconductor is sandwiched between the two P-type semiconductor. The two P-type semiconductor act as a emitter and collector respectively, while the N-type semiconductor act as a base. For NPN transistor, the P-type semiconductor is sandwiched between the two N-type semiconductor. The N-type semiconductors act as a collector and emitter, while the P-type semiconductor act as a base. So in short overview, bipolar junction transistor, both holes and electrons play part in conduction. It is a current control device, but it has two disadvantages. What is that? Low input impedance and considerable noise level. To overcome this limitation, bipolar transistor is gradually be replaced by FET by 1980s, which accelerated the development of logic and CPU units. This is the symbol for PNP and NPN transistor. The major difference is the arrow mark. This for PNP transistor, the arrow towards the base from emitter. For NPN transistor, the arrow away from base to emitter. Basically, the arrow indicates the positive to negative. FET, Field-Effect Transistor. It is a three-terminal semiconductor device. It has high input impedance, low output impedance, less noisy, takes up less space and voltage controlled device. This is the BJT and FET. FET is classified into two types, JFET and MOSFET. It is furtherly classified into N-channel JFET, P-channel JFET, similarly N-channel MOSFET and P-channel MOSFET. So this is the circuit diagram. In this diagram we have the three terminals: gate, source and drain. First we discuss about the JFET, junction field effect transistor. In JFET, the current flow is due to the majority of charge carriers. It is of two types, P-channel JFET and N-channel JFET. For P-channel JFET, the majority charge carriers are holes. For N-channel JFET, majority charge carriers are electrons. It has three terminals: gate, drain and source. Gate terminal plays an significant role in controlling the flow of current through the semiconductor device. The source and drain is a terminal where the current enters and the current exits. The flow of electrons can be controlled by the gate. Already we all know about the depletion layer, right? This is the P-type, this is N-type. The P-type has its lots of holes, positive charge carriers. The N-type has lots of free electrons, negative charge carriers. Electrons from N side depleted or diffuse into the P side. Holes from P side diffuse into the N side. When an electron meets a hole, they recombine and cancel out each other. The N side loses its electron near the junction, leaving behind positively donor ions. Similarly, P side loses near the junction, leaving behind negatively charged acceptor ions. This area lacks the mobile charge carriers. There is no free electrons or holes in this region. This region is called the depletion region. In this depletion region, it acts like a insulator between the P and N regions. Let's see the working. The negative voltage that is applied, the negative voltage applied to the gate, making gate source junction is reversed bias because it is P type positive. The positive is connected to the negative, so it is a reversed bias. Similarly, the positive voltage is applied to the drain relative to the source. This causes electron to flow from source to drain, resulting in drain current. When no gate source voltage is applied, that is VGS is equal to 0, means the depletion regions are narrow, allowing maximum current flow through the channel. But when the reverse biased voltage is applied, it widens the depletion region, narrowing the conductive P-type channel. As the depletion region widens, the effective channel width decreases. The effective channel width decreases, increasing the channel resistance, reducing the current flow from the source to drain. When this reverse bias is increased further, the channel is pinch off, completely stopping current flow. The voltage at this point is called the pinch off voltage. That's why the JFET is called as the voltage controlled device. The voltage at the gate controls the width of the depletion layer. The gate current is ideally 0 because the gate channel junction is reversed bias, giving a JFET a very high input impedance. The graph displays the relationship between the ID, the drain current, and on the y-axis, the drain source voltage, that is VDS, on the horizontal x-axis, the different values of gate source voltage of VGS. This is the linear region where the JFET behaves as a resistor. When the current increases linearly with VDS, this channel is pinched off. This channel is not pinched, the electrons flows easily. This is the voltage at the channel starts to pinch off. Beyond this point, increasing VDS does not significantly increases ID. This marks as a boundary between the ohmic region and the saturation region. The ID becomes almost constant. The JFET operates as a constant current source. Each curve shows the various VGS value -1 volt, 2 volt and 3 volt and so on. As the VGS decreases more negative, the channel narrow more and ID decreases. Applications. The JFET is used as an amplifier, used in audio and RF amplifiers due to high input impedance and low noise. Then it used in analog switches, act as an electronic switch in analog circuits like selecting audio channels. Next, the JFET is act as a buffer, used in voltage follower circuits to prevent loading in previous stages. Next, oscillator circuits. JFETs are used in frequency generation circuits like sine wave or square wave oscillators. Next, low noise amplifiers on microphones, preferred in mic preamps for their low noise characteristics. Last one is a measuring instrument, used in devices like multimeters and oscilloscopes for signal conditioning. An effective way to explain the working of field effect transistor using an analogy of gas stove with regulator control. Imagine a gas stove burner you want to turn on or off and control the flame intensity with a gas regulator knob. The regulator knob used to control the gas flow from cylinder to burner. Likewise, here the gate voltage controls the current flow from source to drain, turning the device on or off and adjusting the flow level. To summarize, Let's quickly recap the main points. Today we explored what the fundamental concepts of field effect transistors, understanding how they function as voltage control devices with high input impedance, low noise and typically occupies less space, making it widely preferred in many modern electronic designs. In essence, understanding FETs gives us insight into the backbone of electronic devices, shaping our everyday life and advances in technology. Thank you for watching.